as will be the handlebar. The EUC weight is 40 kilograms. It's not possible to lift this with one hand. You need to grab this handle and this handle. So the maximum load on this handlebar will be 20 kilograms, I think, because you can't lift the whole EUC up with just one hand unless you are very strong. And it's attached to the metal frames here using two M5 bolts, one here and one here on each side. There's the reason that they use the plastic part. There's so many plastic parts, as you can see here, because when a user crash it, they can cheaply replace the part here. $70 for the whole plastic part. It's still cheap because you still can find it on AliExpress, but 1 or 2 years from now they don't produce this anymore. This part will be very expensive and very difficult to find, so it's a good idea if you can scan this part and reverse and keep it, so one day when you need it you still can print and replace your part. It's a structural component designed to carry the load. Look like it's easy to reverse in CAD, but this part is not easy. This plane is not parallel to this plane in the bottom, and this mounting face is not parallel with this plane. This part is complex, and if I make a cross section here, I can count 1, 2, 3, 4, 5, 6, 7. There are 7 sides on the profiles. So the best idea is to using a loft command, cut the cross section and loft it part by part. I think the original designer, when he designed this part, this end of the handlebar is extend here, and then he used extrude cut to cut his profiles. But when I print this, I'm going to print with the PET CF. Okay, let's get started with the 3D scanning. So this handlebar is symmetry. So when I model this part, I'm going to model only one half. I will mirror it to the other side. To be able to do this, you need to scan the part with the high precision 3D scanner. So if you use a lower precision 3D scanner, the scan on the left and the right will have a different geometry. After you model one half of the scan, when you mirror it, it's not going to match, especially the mounting face here. Number one quality of the 3D scanner is the precision, not the accuracy. You need precision. So when you scan the left and the right side, it must have the same geometry because the part is symmetry. I'm going to scan this in 3 orientation. This side, going to put it upright and slowly turn it. But you can put the clay on if it's not stable. I'm going to do a global marker scanning first. Put it on the point cloud. I'm going to use 0.2 mm for the resolution. Then I'm going to export the global marker. Click on new scan, global marker, import. So this will be the marker that I just scanned earlier. Okay, one more scan. This one, I need to move a bit slower. Global marker, import. Okay, I'm going to fuse the point cloud in a batch process. 0.2, click on OK. There's something different in this version. It's look like that the plane come back after clip it. Or come back. Move to alignment. Click on align. Okay, now it's all aligned. I have 1.8 million points, so I'm gonna mesh to 1.85. Click on apply. Okay, after meshing, it removed the noise from the low quality scan. Okay, next I'm going to export the model in an ASC format, point cloud, and then I'm going to align it using the cloud compare. Okay, this is cloud compare. Just drag and drop light cloud here. Let me change the color. Okay, next I'm going to align this to the XY plane using a 3-point alignment. Okay, now it's aligned. I'm going to rotate this along the Z-axis using the edge of my mirror as a reference. Okay, next I'm going to align this point cloud to the origin point. So the center of the yellow box will be at the origin point. Choose registration, move bounding box to origin. Okay, next I'm going to export this to recap and then put it back into our Inventor. Okay, here's the Odex Inventor, and this is the align point cloud that I import, and it's already in the center of the y-axis. Going to show you the step that I took to model this part. I create two sketches, one here and one here, using a thin slice of the point cloud for reference. And then I use loft command to create a solid model and control the curve by using the 3D lines as a rail. Okay, this will be the second loft. This will be the third loft. So the curve here is made by using a 3D lines. Fourth loft. So until here it's still easy, nothing to consider. Okay, this loft is a bit different. I loft it until here because I know that the original designer, he used his profile to cut it. After he lofted this, I trace the profiles here and use the extrusion cut to cut it. Then I create a plane using the point cloud for reference. Cut out this pocket, so fillet this corner and fillet this corner. And I trace for the position of the two holes here for the M5 screw and extrude cut for the counter bore of the socket head M5. Okay, create a pocket here. This is for aesthetic. It's not serving any purpose for the structure. So I make a fillet here. Next I use the point cloud as a reference to create a plane. So it's this plane and cut it upward for the pocket. Then I fillet along the bottom edge. Okay, make a fillet here. And then I mirror it using this plane as a mirror plane. Mirror it to the other side. This is the mounting face, which is very important. See here, this plane matched the point cloud perfectly. You can see the point cloud here. And on the other side, it also matched perfectly. So it means that one, you need to align your point cloud to the exactly the center of the origin so that you can mirror from one side to the other. And number two, your scan data has to have a precision at least less than 50 microns to be able to do this, because the issue that I found in many 3D scanner, when you mirror from one side to the other, even though you have already adjusted the center of geometry to the origin point, but when you mirror it, one side is not matching the other side. This is because error of the 3D scanner. Okay, this is the filament that I'm going to print with, Kexcelled K7 PET CF filament. The heat diffraction temperature is 80 degrees Celsius. Okay, let's take a look at the strength of the PET CF. I will print the handle in this orientation on the XY plane, and the tensile strength is 80 to 100. If I put safety factors by 2, the allowable load is 40 megapascal. So I put this into a simulation. I assign pin support on the 4 points of the bolt and frictionless on this face. And then I apply the load for 40 kilograms. And if you look at the 1 missing stress here, it's only 26 megapascal. So 26 is much less than 80, and half of 80 is 40 megapascal, so it's very safe. Let's try 80 kilograms here. Let me change it to 80. 53 megapascal. The bearing load on the bolt is still okay, but the maximum load is here, 53 megapascal, which is still okay for PTCF. So the original designer does, I would say, good job for designing this handle. This now will deform under load. Okay, this placement is 1.8 millimeters, so it's still functional, both the strength and deformation. There you can safely use the 3D printed part and replace it with the original part. Okay, I'm in the QiDi Studio. So next I'm going to drop in the step files. I'm going to print this with the 3 layers of the wall. The infill density, I'll change to 25%. This is what I usually do when I print the structural part. And next I'm going to click on the enable support. And it requires 1 hour and 45 minutes. So the top layer won't be looking good because it's going to form steps like this. The load will be applied from the left to the right, so it has to be on the XY, so that I can have 80 megapascal of the tensile strength if I print in this orientation. Okay, let's send this to the printer. I think they have a standard profiles for PETCF somewhere here. Okay, here we go, PETCF. Okay, I have already fed the filament to the tube, and I have changed the tube to the white color. I need to see how far that the filament has been fed into the PTFE tube. Now I have warm up the build plate to 80 degrees Celsius. Chamber temperature 55, bed 80, and also 280. Now I have a problem. It has layer separation. The part is still sticking onto the bait, but I can see that there is a layer separation. QiDi Q2, it cannot finish the PTCF. You see here, it separates the layer. Okay, I will stop the printing and I move to the Creality K2 Plus. See if it have this same issue. There's a lot of stringing. I have already dried filaments. I mean, I dry it and then I put it in a vacuum seal bag. Okay, the K2 Plus can finish the print 1.5 hours. Okay, let's take a look at the print from the QiDi Q2. Maybe you can put in a comment what you think, why it has a layer separation. Yeah, about here, it starts to suddenly, it prints fine from the bottom layer until here. I don't see what triggered this printing failure. It's like it's not adhering to the layer before it. The nozzle temperature is too low. You can just peel it off like this. The print from the Creality K2 Plus is K2 Plus, and this one is QiDi Q2. I don't see any indication of the failure in the same layer height from the K2 Plus. See, about here there's no indication of the failure, but you can see that it has a rougher surface on the Q2, but from the K2 Plus it's very smooth. I already know that the PETCF is not good at printing with the overhangs, and the support removal is very difficult. There's a defect on the tip of the handlebar here, and it also appears in the same spot as the K2 Plus. It's a corner. Maybe it's a pressure advance setting, because with the QiDi Q2 it also has the defect in the same spot. Wet filament is not the issue here, because I know when it wets it's going to print with small bubbles, but this one has no bubbles. Okay, this is the print that I test with the PETG. Very easy to print. There is no defect, and the support removal is easy. I can just pull it out from the build plate and use it. And it feels very good in hand. Very similar to the original part, because this one is, I can feel it is very abrasive, while the PETG feels much better. But the tensile strength of PETG is 50 megapascal, comparing with this one, which is 80. It's 60% stronger than PETG. This one is stiffer than PETG because it has carbon fiber. I find that this filament is quite difficult to print. A lot of post-processing, sanding and collecting the defects, but its strength outperforms the other filament that I have. Thanks you guys for watching. I'll see you in the next video.